Hello friends. In today's class we are going to talk about basic of memory management. Welcome all of you, and we are starting a new topic here, that is your memory. And we are talking about here anything that is related basic with memory, means basic points related with memory. So this is our computer organization here in this case, and you identify that within the CPU there are few units are there, which is really very important. So right now our main concern with this unit, that is called memory, and this is the entity that is CPU, and this is the entity that is your IO. So these are the three fundamental components of computer system. And within this fundamental computer system, you identify that there are few registers are there, like here MAR, that is your memory address register, and that is connected with your address and this bus. Okay, so there is an address bus. Okay, an address bus. So what address bus does is it sends the address. Where it will send the address? It sends the address to the memory. Then we have another data structure, another register. Extremely sorry for this. Then we have another this register that is called memory data register, that is connected to MDR. Okay. So now before I go to this another registers, MAR and MDR basically is the interface. It is the interface of CPU with memory. Okay, so directly it does not communicate with memory, it communicates through this address and data register. Then you have another register that is called program counter, PC, and IR is the instruction register. Okay, so now a few more points here. In this case, this is your arithmetic and logic unit where operation will be performed, and we have a set of control unit. CU is for control unit. Then we have another register. This is called accumulator, and another register. And then we have a general purpose set of registers. Okay, this is a small computer organization. Now suppose if I go with this for explaining you more, that if I have an instruction here, in this case suppose add R0 and R1, which is interpreted as R0 will be loaded with R0 plus R1, and suppose this address is 1000. Okay, now here this is the starting address, so PC will contain 1000. Okay, PC will contain 1000. What PC contain? The address of the next instruction to be executed. Okay, address, always it will contain this part, address of next instruction to execute. Okay, so now this address PC, I'm saying that in terms of event, that PC will be loaded in MAR 1000, and then it will be sent to the address, will be sent to here in memory, and here in memory it will read the location 1000, which is add R0 and R1. So in this case, this add R0 R1 will be read, and it will be put into this add R0, its bit equivalent, and it will put into the MDR, add R0 and R1. Okay, so this is the event, and this is why this MAR and MDR are important. Finally, this address add R1 will be loaded into instruction register. Why? For execution purpose. So finally this instruction register will execute that part, and that is your MAR and MDR, memory address register and memory data register. Okay, so this is a more broader diagram, only concentrating on MAR and MDR, and the purpose I already told you, that these are registers, and the main purpose of these registers is interaction with memory. Okay, so this slide is a redundant slide. We don't have anything in this, and interaction with memory. Okay, So now in the previous slide you have talked about address bus and the data bus, and these are the two very important factors that decides your memory, address bus and data bus. Okay, so now address bus will send the address. We have already seen that address bus sends the address. Okay, now here suppose address bus is of size, let's say 4 bits. For simplified reason I'm taking 4 bits. Then this address bus can send the address 00000001 0010 0011 0100 0110 and 0111 up to finally 1111. So this is the range of the address that it can send if there is a 4-bit of address bus. So here for this memory, what we are going to do, that we are going to have this location, the first location as our 0000. The next location of the memory will be 00001, and the last location of the memory will be 1111. Okay, so when it will send that, suppose it is sending the address something like 1111, then it will go to this particular location. So that is the address bus. So if the address bus, now the generalization is this, that if the address bus size is 2 to the power, if the address bus sizes of n bits, okay, address bus is of size of n bits. If address bus is of size n bits, okay, then number of memory location possible, okay, number of memory location accessible, number of memory location accessible will be what, 2 to the power, and in that case the first address will be 0 1 and the last address will be 2 to the power of n minus 1. Okay, so that way. So that is your address bus. Now the second entity here is the data bus. Okay, data bus. Okay, the second entity here in this case is the data bus. And in the data bus is concerned more with this part here. The data bus is concerned with more of this part, that what is the size of this location. Okay, now address bus is of what? Address bus is about number of locations. Okay, number of location. And data bus, when you talk about, that is nothing related with the quantity, that is size of each location. Okay, size of each location. Okay, so I'm talking about what is the width of this one. Okay, what is the width of this one? And that is not mandatory, that it is not mandatory that this size, one addressable location size, it is not mandatory. Addressable location size is equal to your data bus. That is not mandatory. Okay, but minimum size I'm talking about. The minimum size should be what? Suppose this location is of 1 byte. Okay, that means 8 bits. Okay, so when you are accessing this location, 8-bit information can be accessed, and this data bus should be size, okay, size of at least 8 bits. At least 8 bits. So this should be size of at least 8 bits. So that is the how it has been defined, address bus and the data bus. The first location is of size. The first location and for the first entity, address bus is about how many locations are there, and that is 2 to the power 1 location. And database is about size of each location, that how much this space is. So now memory excuse me, memory is a 2-dimensional entity. Memory is a 2-dimension entity, where the first dimension is the row 1, the row part. Okay, this row part, and that is nothing but given by the address bus. And the second dimension here in this case is the column part, and which is nothing but your size of each location, and together size of each location together they define the memory. Units can be what? Units are the basic smallest unit is a bits, and that can be either 0 or 1, or we can group them in byte. That can be the smallest unit, that is group of 8 bits. Okay, word size depends upon the system. Okay, word size depends upon the system, and in general group of 4 byte constitute a single word. Okay, so that is the standard one, that group of 4 byte constitute a single word. But generally this in purpose of the examination we have to be flexible with this. Now the important term here in this case is a byte addressable or word addressable. Okay, so what we have already seen here in this case is that if there are n bits to address, then there are 2 to the power n locations possible. Okay, 2 to the power n location possible. Okay, that is 0 to 2 to the power n minus 1. Now if the system is a byte addressable, then each location will be consist of 1 byte. Each location will consist of 1 byte information. One will also consist of 1 byte location. So byte addressability means 1 byte will be assigned 1 address. Okay, now each byte will be this 1 byte. Each address will be 1 byte of size. Word addressable is something that same parameter, but instead of having a single byte here, now what will happen is this: each location will become the size of one word, and that will become 4 byte. Okay, so 1 word, 1 byte is assigned 1 address is 4 byte or 1 word. Okay, so byte addressability is 1 byte will be assigned an address, and word addressability is 1 word assigned an address. Right now this thing will impact your size of the main memory. Okay, so size of the main memory will be greatly impacted because of this. Okay, so what is exactly the size of main memory? Two to the power, here I will write number of bits multiplied by addressability that means what size assigned 1 address. So this is the size of the memory, and the next part here is a question related with this, and it says that a processor can support address bus of size 16 bits where memory is word addressable with the word size of 2 byte. The size of the memory of the processor is blank bytes. Okay, so what is the formula here? Size of memory is equal to what? 2 to the power number of bits, here in this case is 16 bits given to you, multiplied by addressability, and here this formula I'm using, this one. So multiplied by addressability, and here word addressable with word sizes 2 byte. Okay, so that will become 2 to the power 6 you can take it out, even 2 to the 2 you can take it out, into 2 to the power 10 byte, and that will become 2 to the power 7 kilobyte. That will be 128 kilobyte. The total size of the memory here in this case is 128 kilobyte. This is the next question, and it says that it can support maximum memory of 4 GB. Okay, so memory size is given to you 4 GB, where 4 into G stand for 2 to the power 30 byte. Where memory is word addressable and size of the address bus is at least 2 to the power, here I will write size of address bus, and memory is given as word addressable with 2 bytes. So this is my equation, and what I can say here is this 2 and this 2 will be gone, and that will become 2 to the power size of address bus will be equal to 2 to the power 31, and now I can take the powers equal and it is base is equal, so size of the address bus will become 31 bits. Okay, so that is for this. Now we generally view the memory abstractly as a single unit. That means we believe that memory starts with this, memory look like this. Okay, we believe that memory is abstractly look like this, and always we say that this is the location number 0, this is the location number 1, this is the location number 2, and with that we grow up to what, location number 2 to the power n minus 1. Okay, so we believe that it's a one dimension array, and we also believe that it is a contiguous memory. Okay, so this is our abstract view, and then we believe that this is the place where it will be stored. Okay, so this will be place where it will be stored, and here the address. So that is the abstraction, and that is what we believe. But actually it is about constructed with your chips, the random access memory chips. Right, and we have a chip select 1 active high and chip select 2 active low. There is a read and write is the control signal. Okay, read and write control signal. Okay, that you want to read. So you have to first activate, and there is a 7-bit address. Okay, with the 7-bit address, what you can say that there is a location 0, 1, 2, and up to what, 127. Now we have to give the control signal what you want to do, and it says that 8-bit data bus. Okay, so that means one location here, the chip consists of 8-bit in this case, 8 bits. Okay, so that is actually how does it look like, and we have a active low. So to read and write operation, you have to either you give the chip select this one, or you give the active low chip select. You give the address, send the control signal, read and write, and 8-bit data will be into the database. This is how it has been organized, and here suppose we have decoder, address decoder is there. So A0 to A3, there are 4 bits we are sending into the decoder, and here we have organized as 0, 1 up to 15, total 16 rows are there. Okay, 16 rows are there in this case that can sense read or write operation, and we have B0, B1 and up to B7. Okay, so 16 memory locations are there, word number 0, word number 2 to word number 15, and each location consists of B0 to B7, that is your 8-bit of information. That is much more broader view of this. Inside you can say what exactly inside in that. So this A7 that is written over here is basically, it is consist of what? It is consist of a decoder. Okay, A0 that is written, A7 written here is consist of a decoder. Fine. Okay, so that is how it has been organized. Now what we can create larger memory by using chips. Even if you look at your RAM, okay, even if you look at your RAM, then you will find that there are many chips are present over here, okay, and these chips are your module chips or banks. In your RAM this is called module chips, or it is also called as memory bank. If you look at this diagram, we have an active low, active high CS1, active low, then there is a read signal and there is a write signal, and then we have A1 to A7 as your A1's A7 signal here, and 128 cross 8 bit is the organization. Instead of one RAM, we have 1, 2, 3, 4, and here up to here is the RAM. It's a ROM, sorry. So we have 4 RAMs here in this case. Okay. So what is the idea here? What is the idea here in this case is that here 1 to 7, and fine, it is a 7 bit is used for this decoding this address within this chip. Okay, 1 to 7, 128, which location we are talking about. Now look, if you look at this 8 and 9 bits of this, okay, 8 and 9 bits of this. So now we have 1 to 16 as our address bus. Among this 1 to 7 is used for address within the RAM, and 8 and 9 is used to decode this thing. And what is the output of this decoder is for this active high CS1, active high CS1, active high. So that means this decoder is basically working as a selection of which RAM chip data will read or write. So this is working as a selection mechanism in this case. Okay, 8 and 9. And 10th one is, if you say, that is your active low CS2. So now we have means instead of this should be active high, this should be active low, or we can exclusively also use this thing. Okay, and this is your data bus that will be taken by this. So this is how we create a larger memory by using your RAM chips. Okay, so that is the exact view, you can say, of this memory or random access memory. Actually it is look like this. So I presented here 3 diagrams for you, and that is how it does look like. 11 to 16 is the data bus that has been not used in this particular case. So we are talking about explicitly memory, and we must know that what are the issues that memory management is dealing with. So the main thing that memory management deals with is the allocation, partition into a different, let's say, segment or pages, protection, that protecting a process from one another, free space management, memory management, and deallocation. Allocation, partition, protection, free space management, and deallocation. This is the responsibility, or you can say function of memory management. We can say explicitly responsibility. Okay. Goals, that we want to utilize our space, and that is the main thing, that we want to run a larger program in a smaller memory. That is the basic concept of what? Virtual memory that we want to achieve. Lowering the overhead, reduce the effective access time. Okay, so utilization, lowering the overhead, and effective access time. So that is the memory goals of the memory management. Okay, so in the next section we are going to talk about statically and dynamically linked libraries. Okay, so that's all for this section. I hope you understand and enjoy this session. Thank you.